Good morning. So I've owned a theodolite for a few years now, and one measurement that I didn't get around to doing with it was a reciprocal zenith angle measurement. I do have a video on my channel where I did kind of a poor man's version of it using an auto level. So I thought just to add to the body of work, I thought I'd get out and do it. So the idea is that we set up two theodolites a decent distance apart and point them at each other and measure the vertical angle from zenith. So if we lived on a flat earth, then the verticals for each theodolite, which are the black lines here, would be parallel. And if you know your geometry from primary school, you can easily see how this leads to the result, where the sum of these angles is going to equal 180 degrees. But we're looking through an atmosphere, and that atmosphere has a gradient, which typically gets less dense as you get away from the surface. And that changes the path of light, which changes the angles that we measure. Now, this is obviously not to scale, but this would mean on a flat Earth, the sum of these two angles would actually be less than 180 degrees. But if we're on a globe, then the verticals of those two theodolites are not parallel. They diverge by a little bit. So again, this diagram is obviously extremely exaggerated, but you can see how these diverging verticals means that the sum of the two angles will be greater than 180 degrees. And even with refraction, which reduces the zenith angle by a little bit, the sum of the angles will still be greater than 180 degrees. And that's what we're going to go test. So here's a sight line not far from my place, which is just under 5 kilometers. And the vast majority of that sight line is well above the surface, which means we don't need to worry about extreme refraction in either direction. And here's the first measurement I made. It was over on North Head. So I set up my theodolite a few meters away from those red and yellow garbage bins, and then adjusted the height of the theodolite until it was within a couple of arc minutes of the top of the bins, and then pointed over towards Mossman to see what I could see. And I ended up pretty much at random choosing this dude's front fence. And I have to say it's incredibly difficult to hold an iPhone up against the eyepiece without actually pushing on it. So this is about the 10th attempt at getting a photo of what I was seeing through the eyepiece. And here are my two measurements. So you take both a forward measurement and a reverse measurement, and then take the average of them, and that reduces the error. So the average of these two measurements came out to be 90 degrees, 19 minutes, and 36 arc seconds. And then a few days later, I went over to that dude's place and set up out front and made the shot back towards North Head. And here's that shot. And you can see the red, yellow, red bins a little bit to the left of the crosshairs. And here are the forward and reverse angles. And again, averaged out to reduce the error. And we get 89 degrees, 42 minutes, and 30 seconds. And what do you know? If you add them together, you get more than 180 degrees, which immediately falsifies flat Earth. But what kind of excess do we expect on a globe? Well, this is pretty simple. We just take the proportion of the circumference that we're measuring over. So the sight line was only 4.671 kilometers out of a total circumference of 40,000 kilometers. Then the amount of curvature we expect is 2 minutes and 31 seconds. But we do have an atmosphere, and that has the effect of slightly reducing our zenith angles. And the way we account for refraction in the geometry is by increasing the radius of the sphere. So with refraction, the predicted result is 2 minutes and 10 arc seconds, which is incredibly close to the actual measurement of 2 minutes and 6 arc seconds. And my theodolite claims an accuracy of 2 arc seconds. So I'm pretty stoked with that result.